Hey everyone, and welcome! So, take a quick look around you. I bet you can spot a circle, right? The wheels on a car, the face of a clock, maybe even the top of your coffee mug. Circles are literally everywhere. They're one of the most basic, fundamental shapes in the whole universe. But how well do we really get them? Today, we're going to unlock some of their coolest secrets.
Okay, so picture this for a second. A skydiver, just hanging out 3 kilometers above the Earth. What do you think that view is like? How far can she actually see before the Earth curves away? Now, this isn't a trick question, it's a math puzzle, and the key to solving it is hidden in the geometry of circles. This is what I love. It shows how math isn't just about numbers. It's a language for explaining our world.
So, to tackle problems just like that one, we are going to build ourselves a toolkit. And look, this isn't about memorizing a bunch of dry rules for a test. No way. We're adding 3 super powerful, unbreakable tools to your mental kit. Once you have these, you'll be able to look at pretty much any circle problem and know exactly how to break it down and solve it.
All right, let's grab our first tool. This one is all about a very special kind of line, one that interacts with a circle from the outside. It's called a tangent.
A tangent never actually crosses into the circle. It just kind of grazes the edge. The best way to think about it is a line that comes up and just kisses the circle at one single, super precise spot. We call that the point of tangency. Then it just keeps on going. It never breaks the surface.
And here's where the magic happens. This is the rule. If you draw a line from the very center of the circle, that's the radius, out to that exact point of tangency, they will always meet at a perfect 90-degree angle, perpendicular, every single time. This isn't a sometimes thing, it's a core property, and it is the key to so much.
And that's not just some fun fact, This property is absolutely essential. That 90-degree angle is like a giant flashing sign. It tells us that we can create a right-angled triangle, which means we can bring in one of the most famous and useful tools in all of mathematics.
You got it. That 90-degree angle is our invitation to use the Pythagorean theorem. As soon as we see it, we can form a right triangle, and once we have that, we can use our old friend a squared plus b squared equals c squared to find any missing side length we need.
Okay, tool number 1 is in the bag. Let's move on. For our next tool, we're going to leave the outside of the circle and head inside to check out these lines called chords.
So, unlike a tangent that just grazes the outside, a chord is a straight line that cuts right through, connecting any 2 points on the circle's edge. And a little fun fact for you, the longest possible chord you can draw is the diameter, because it's the one that passes right through the center.
Now here is the secret to chords, what we're calling the chord code. If you draw a line from the circle's center so that it hits the chord at a 90-degree angle, it will always slice that chord into 2 perfectly equal pieces. It bisects it. This is our second golden rule.
So, how is this useful in the real world? Well, let's solve a little puzzle. Imagine you've got a big circular pipe with a 20-centimeter radius. There's some water sitting at the bottom, and the flat surface of the water, from edge to edge, is 24 centimeters wide. The question is, what's the maximum depth of that water? It seems kind of tricky at first, but our new tool makes it easy.
Let's break it down. First, we realize that the water's surface is a chord, and it's 24 centimeters long. We know the radius is 20 centimeters. Now, let's use our chord code. We draw a perpendicular line from the center down to the chord. Bam! It bisects it, splitting it into 2 12-centimeter pieces. And would you look at that? We've made another right triangle. We can use Pythagoras again. 12 squared plus our unknown side squared equals the radius 20 squared. A little bit of math, and we find that unknown side is 16 centimeters. But wait, we're not done. The whole radius is 20, so we just subtract that 16 from 20 and we get our answer. The water depth is 4 centimeters. See how that works?
All right, time for our final tool. For this one, we're staying inside the circle to look at the amazing, super predictable relationships between angles. This is where circle geometry gets really, really elegant.
First things first, we need to meet the 2 main players here, the central angle and the inscribed angle. It's simple, really. A central angle has its pointy bit, its vertex, right at the center of the circle. An inscribed angle has its vertex somewhere on the edge of the circle. That's the only difference, where the point is, but it changes everything.
So, here it is, the big rule. If a central angle and an inscribed angle are both created from the same 2 points on the circle's edge, if they're subtended by the same arc, there's a beautiful, simple relationship between them. The central angle is always exactly double the inscribed angle. I call it the 2-for-1 rule. It's great because if you know one of them, you automatically know the other.
And this one rule leads to a couple of awesome bonuses for our toolkit. First, it means that any inscribed angles that share the same arc are always going to be equal to each other. And second, this one is super useful, any angle that's inscribed in a semicircle is always a perfect 90-degree right angle. These are incredible shortcuts.
And that's it. In just a few minutes, we've put together an incredibly powerful toolkit. We've gone from just looking at a circle to really understanding how it works from the inside out. Let's do a quick recap of the tools we've collected.
So here's what's in your new toolkit. You've got the tangent radius rule, which gives us that all-important 90-degree angle. You've got the chord code, which lets us slice chords perfectly in half. And you've got the 2-for-1 angle rule, linking those central and inscribed angles. If you can master these 3 simple ideas, you've pretty much got the keys to circle geometry.
So now you have the tools. You could totally go back and solve that skydiver problem now. But it's about more than that. Now you can start to see these rules and relationships all around you, in the gears of a bike, the design of a logo, or even the simple curve of the Earth's horizon. So the real question is, what hidden geometry are you going to find?